thanks for watching. And today I would like to prove a very crucial fact about determinants. Because so far we define determinants as being an expansion along the first row. How do you know it gives you the same answer along any other row? And that's the point of today's video, is to show you that indeed, if you expand it along any other row, you get the same answer. And it's based on this really neat fact, so just a key lemma, which I'll show at the end because the proof is very messy. Namely, suppose the ith row of A is of the form Ej. Ej, which is just of the form 0, 0, 0, dot, 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 1, 0, 0, so in the jth entry. In other words, suppose A looks like this. A is, I guess determinant of A is simply in the ith row and the jth entry, you have a 1, and everywhere else is 0. Then the question is, what is the answer? What should that determinant look like? And remember, we're not allowed to expand along the ith row yet. But suppose it's true that we can expand along the ith row. Then the answer would be, you see, here you start with -1 to the 1 plus 1. You jump to the ith row to get -1 to the I plus 1. And then you jump to the jth row column and you get -1 to the 1 plus j. So the answer should be -1 to the I plus j times 1 and the determinant of the rest, which we usually call that submatrix, you call Aij, so it's just the determinant of Aij squiggle. So in other words, assuming only that we can expand along the first row, this fact holds, which should hold if we can expand along the ith row. And in fact, it's this crucial lemma and multilinearity that helps us find whether the determinant is independent of the row expansion or not. And in fact, let me show this first, and then I'll show the key lemma. So theorem. For all I, from 1 up to n, the determinant of A, it's simply what you get if you expand it along the ith row. So if this is A11, A1n, AI1, Aij, Ain, and then An1, Ann. If you expand it along the ith row, then you get the sum over the columns of this -1 to the I plus j, which I talked about, then the ijth entry, which is Aij, times the determinant of the rest. If you do that, you get determinant of Aij squiggle. In other words, if you expand it along the ith row, it's the same thing as expanding it along the first row. And why is that true? And again, nice thing is we don't need any definitions for here. We just need, beautiful multilinearity. So notice A, the determinant of A, is just the determinant of the matrix whose rows are the matrix rows of A. So it's the determinant of A1, dot, 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 AI, up to AN. And this I is not random, it's the row we want to expand this with. But let's look at this term. AI, by definition, that's AI1, AI2, AIN. But now we want to use our key lemma, which says we need some row of the form E1 up to En. But we can do this because this is AI1 E1 plus AI2 E2 plus up to N AIN En. And that's good because if we can somehow write this in terms of E1 up to En, we are done. I mean, not we're done, but we can use the key lemma. Because then, what is the determinant of A? The determinant of A is the determinant of A1, AI up to AN, which is the determinant of A1, and then AI1, E1, plus plus AIN, EN. That is the ith row. And now notice, well, those are vectors, those are just scalars. So we just get a linear combo of E1 up to En. Now, if the determinant were linear, it's nice, we can put all the constants out, but even though it is not linear, it's still nice. It's what's called multilinear, which means it's linear in every row. So in particular, multilinearity applied n times allows us to just pull out the constants. That becomes AI1, determinant of A1, E1, AN plus AI2 of the same thing up to AIN of A1, EN. Sorry, no, not at the end, but at row I. So all those things, they're done at row I. But now, why did we do this? Remember, if one of the rows of your matrix is of the form E something, the answer is the same as if you expanded it along that row. So, then, by our key lemma, or I guess first let's write this in terms of summation. So this is the sum from J, from 1 to N, of Aij, of that determinant, A1 up to Ej, up to An. That's the ith row, I like to remind you. And then, by what I said, so by this key lemma, the answer is then just minus 1 to the I plus j, and then the subdeterminant. But the subdeterminant of this, it's precisely the determinant of Aij, squiggle. Because what does this matrix look like? It looks like, A11, A1n, and then in the ith row we get 0, 0, 0, 1, 0, 0, 0, and an1 up to an. So this is I, this is j. And look, if you eliminate this row and this column, the matrix A is like unchanged. So this is precisely the same thing you get as if you remove the ith and jth row and column. If you remove the ith row and the jth column of A. That's why this submatrix, it's precisely Aij squiggle. Because really the only modification we did to A is we changed the ith row, but we eliminate that in the row expansion. And then notice, this is precisely what we want. It's a sum from j from 1 to n of minus 1 I plus j, Aij, and Aij squiggle, which is precisely the cofactor expansion along the ith row. So if we can prove this key lemma, then we're done and we can go home happy. And now let's prove that key lemma. And I'm terrified because it's a difficult proof, but let's see if we can do this. And by the way, if you're my student and you're watching, you don't need to know the proof of that key lemma. This is already enough, I think. Okay, and let me change notation slightly because I'm using I and J just to fix things. So claim. So if row I of A is of the form, let's say EK, because I want to use J for something else. Form EK. Then the determinant of A, it's the same thing, minus 1 I plus K of the rest. Squiggle. All right, and first of all, notice this is clear if I is the first row. Because if the first row is of the form EK, then just cofactor expand along the first row, which they can do, and it gives you the answer that you want. What makes this hard is that we don't know what to get when we expand along the ith row. And for this, let's use induction. So first of all, note, so assume I is not 1, so I is greater or equal to 2, and we want to do this by induction on n. On n, so assume, suppose it's true for n minus 1 times n minus 1 matrices. So show true for n times n matrices. All right, and I forgot, like the base case is n equals 1, and well, the only case for this happens is for the matrix 1, and this is true, so n equals 1 isn't too bad. But now, let's assume we have a general matrix, okay? So we have a matrix, and in the row I in column K, we have a bunch of zeros and then a 1. Then, if A is n by n, well, if you cofactor expand along the first row in the jth column, we get the definition is just sum from j from 1 to n minus 1 of 1 plus j a1j squared. All right, and one thing. So suppose this is column J. Suppose J equals K. So suppose we expand it along this column, and then suddenly we expand along this column. Then notice the resulting submatrix has a row of zeros. And you can show, I think exercise if you want, that if a matrix has a row of zeros, then the determinant is 0. I think you do induction if you want. And so in particular, if J equals K, there's nothing in your determinant, which means that this sum skips K. So we only need two cases if you want. J is less than K, and then J is greater than K. So this is the sum of J less than K minus 1 to the 1 plus J, A1J squiggle plus, and you'll see why we need this distinction. Sum J greater than K of minus 1 to the 1 plus J, A1J squiggle. All right, as if this is not enough, let me introduce some more notation. Because notice this A1J squiggle it's a smaller matrix, right? So in particular, we can apply induction to our A1J squiggle, because in a second I'll show you. It has the same form, and as I said, a little bit more notation. So remember, row I and column K, those are fixed. So suppose first of all, you remove this. And you will see in a second, if you remove the first row and the jth column, then you get an even smaller matrix. And that matrix of just all the rest that happens when you remove the ith row, the kth column, the first row, and the jth column, we call this B1J. So it's simply what is left after doing this whole Bomberman thing. We call this B1J. And you'll see why. Now, notice when you calculate A1J squiggle, then we remove the first row and the jth column. So what happens? First of all, if j is less than k, so suppose you take k, but you remove the column that is before k. Then the problem is the placement of this one gets shifted by 1. And not only that, we remove the first column, so 1 and j. So what happens? First of all, you have a smaller matrix. You have an n by n minus 1 times n minus 1 matrix. And the question is, where does this 1 land? First of all, you remove the first row, so this row I will become row I minus 1. Kind of this one gets shifted up because we don't have the first row anymore. And also, because j is less than k, this one gets shifted to the left. So the new position of this one, it's in the I minus first, comma k minus first entry. Now, so in particular, this submatrix, A1J squiggle, it's indeed a matrix of the same form, because one of the rows is of the form ek minus 1 here. And in particular, this is why we assume that I was bigger than 1. Otherwise, you may eliminate that thing. So in particular, we are in induction land, so we can apply our induction hypothesis. So for the first sum, it becomes the sum j less than k minus 1, 1 plus j. And what does our induction hypothesis say? It's minus 1 to whatever this position is of the determinant of the rest. So here, the other position is the I minus 1 plus k minus 1 position. And then very interesting, what is the submatrix? Well, sorry, wasn't I? Yeah, I have A1J squiggle. So, what did we do? So, to get A1J squiggle, we eliminated the first row and the jth column. And then the induction hypothesis said it's whatever matrix you get by eliminating the ejth row and the ekth column. So, if you eliminate the first and the jth column, and you further eliminate, if you want, the row of the e's and the column of the e's, then you're left with precisely this B1J, which remember was the rest of everything. So this submatrix that's left over, it's precisely B1J. And what you do then is just take the determinant of this rest, which is the determinant of B1J. All right, that's good. And notice there's a simplification. Minus 1 to the minus 2 is just 1. So basically, those things disappear. And you're just left with 1 plus j plus I plus k. Now, slightly more difficult. I hope you're not quitting, but if j is greater than k, actually no, I shouldn't have said that. It's easier, I think. Because that was the situation where j was less than k. Now suppose j is bigger than k. So again, suppose this is your k, we have 0, 0, 1, okay, and then suddenly j is bigger than that. Then, if you remove the first row in the jth column, the submatrix will still be of the size n minus 1 times n minus 1. The ith row will become the I minus first row because we have a minus here. So in other words, the what's called the placement of this EI or something will be one row above. But notice the column will still be the same because if you eliminate this jth column, this column k will be intact. So the point is, this 1 will be still in the kth column, but in the I minus first row, which means it's almost the same thing. And again, matrix of the same form, so by induction, but this time the entry will be minus 1 I minus 1 plus k. And then the rest is still the same. You're eliminating the first row and the jth column, and further taking the determinant of the rest. So what's left is those crumples, which is just B1j. All right, I know, quite intense, but now we can just move on. So here's where we applied our induction hypothesis, and then notice this is a sum over j, so whatever doesn't depend on j we can pull out. So for example, we can pull out this minus 1 to the I plus k times sum j less than k of minus 1 to the 1 plus j determinant of B1j plus, notice this minus 1 to the I plus k, this thing also comes out as the same factor, and what you're left with is the sum of j greater than k of minus 1, and you'll see why I write it this way, minus 1 to the 1 plus j minus 1, and then B1j. And close the parenthesis. Now, if a number is strictly less than 4, it's less than or equal to 3. So this j less than k is just j less than or equal to k minus 1. And same thing here. J is less than or equal to k plus 1. So in particular, j minus 1, it's greater or equal to k. So if you want, here just do a change of variables and let j prime be j minus 1. Then, you're left with the sum minus 1 to the I plus k sum j less than or equal to k minus 1 minus 1 to the 1 plus j B1j, and then plus sum j, if you want j prime greater or equal to k of minus 1, 1 plus j prime, and b of 1, so j equals j prime plus 1. So if you want j prime plus 1. But you see here, j prime is just a dummy variable, so it's like doing, if you do an integral with respect to u, f of u du, It's the same thing as the integral of f of x dx. And therefore, just remove this prime. So this is like going from u to x again. And it turns out this thing is actually a much easier thing. All right, and my apologies, I realized there was one term I forgot in our sum. I forgot about the A1j's. So the sum that we had from the determinant of A became minus 1 to the I plus k, sum of j less or equal to k minus 1, minus 1 to the 1 plus j, A1j, determinant of the rest, B1j plus the sum from j greater or equal to k of minus 1 to the 1 plus j, A1, j plus 1, and B1, j plus 1. And I'm claiming that this thing is actually equal to minus 1 to the I plus k of the determinant of aik squiggle. And once we prove that, then we are done because that's exactly what we wanted to show. Now, here's why it's true. So suppose A is of the form A11, and then A1j, and then A1 k, A1 k minus 1, A1 k, A1 k plus 1, and then another one, A1j, you'll see why, A1n, and then it has just 0 here. The other terms, and that's in the ith row and kth column. Now, what is aik squiggle? It's just you remove the kth column and the ith row. So aik squiggle looks something like that. That is, again, A11, A1j, A1, k minus 1, and then A1, k plus 1, A1j, and then A1, and yeah. And also the ith row disappears, but that's not the point of this. All right, then suppose you want to evaluate the determinant of that. Then you would just do a bunch of row expansion. So you expand it along the first row. And in the case, so this is kind of k, in the case j less than k, you do minus 1 to the 1 plus j, a1j times some subdeterminant, which you have here. But in the case j greater than k, I guess j greater or equal to k, here's why. So this is the k minus first entry, and this is the kth entry. So now, if j, if you want, is greater or equal to k, then the kth entry is a1 k plus 1, and then here, the jth entry of this becomes a1 j plus 1. You see, because here, from the right, everything gets shifted by 1. And that's why the jth entry here, it's precisely a1 j plus 1. So the only thing left to figure out, what about the b1j's? But remember, what was it? So to get aik squiggle, so you take this row 0, 0, 1, 0, 0, you eliminate that. And then, if you want to row cofactor expand it, then you would expand it along the first row and the jth column. Then what happens? You eliminate the first row of A, but also the jth column, which in your picture looks kind of like this, 1 in j. So really, in this case, what you end up with is the determinant of b1j, because b1j is just the rest here. On the other hand, if j is greater or equal to k, then you don't really eliminate, you do eliminate the jth column of this matrix, but the jth column of this matrix is the j plus first column of A. And that's why if you eliminate the j plus first column and the first row, the ith row, and the kth column, what you end up with is B1 j plus 1. And that's exactly what you get here. So if you expand this determinant along the first row, you get precisely this expression, and that's why this is a determinant, and therefore we're done, and we can go home happy. All right, I hope you like this. My voice has disappeared. I hope you like this determinant extravaganza, and from now on, you can expand the determinant along any row you like. But you can't expand it yet along every column. That's the point of another video. Alright, again, thanks for watching. I hope you like this, and please make sure to subscribe to my channel and click the notification bell. Thank you!